What specific problem does LLaVA-Scissor aim to solve in the context of video large language models, VLLMs, and how does it differentiate itself from existing token reduction methods?
LLaVA-Scissor addresses the problem of excessive redundancy in visual tokens generated by video large language models, VLLMs, during video processing, which hampers computational efficiency and model performance. Unlike existing token reduction methods that often focus on segmenting videos or rely on attention scores to select key tokens, LLaVA-Scissor employs the Semantic Connected Components (SCC) strategy to identify and retain distinct semantic regions across both spatial and temporal dimensions. This approach allows LLaVA-Scissor to capture a comprehensive representation of video content without redundancy, as it aggregates tokens from non-overlapping semantic regions rather than merely selecting key objects. Additionally, LLaVA-Scissor's two-step compression process first compresses tokens spatially within frames and then further reduces redundancy temporally across frames, enhancing its effectiveness compared to other methods that overlook temporal relationships. The results demonstrate that LLaVA-Scissor consistently outperforms other token compression approaches, particularly at lower token retention ratios, by preserving essential semantic information more effectively.
How does the proposed Semantic Connected Components (SCC) strategy work? Please illustrate the methodology step by step, including how it computes the pairwise similarities and constructs the graph for token compression.
The Semantic Connected Components (SCC) strategy operates through a systematic approach to identify distinct semantic regions within a token set. First, it computes pairwise similarities between tokens, resulting in a binary similarity map, A, where Aij indicates the similarity between tokens, K_I and K_J. This map is treated as an adjacency matrix, allowing the construction of a graph where each token is a vertex connected based on their similarity. Next, the SCC strategy employs a union-find data structure to identify connected components within this graph, effectively partitioning the tokens into non-overlapping regions. Finally, each connected component is aggregated to form a representative token, thereby compressing the original token set into a reduced set that encapsulates all unique semantic regions without redundancy. This method ensures that the compression captures comprehensive semantic information, while disregarding positional adjacency among tokens.
Can you provide a simple example to illustrate the process of token reduction using LLaVA-Scissor, detailing how distinct semantic regions are identified and selected for representation?
To illustrate the token reduction process using LLaVA-Scissor, consider a video with 3 frames, each containing distinct semantic regions: a dog, a park, and a person. Initially, each frame generates multiple visual tokens representing these elements. The first step involves applying the Semantic Connected Components (SCC) strategy, where pairwise similarities between tokens are computed to identify unique semantic regions. For instance, tokens representing the dog in all frames are grouped together, while those for the park and person are similarly clustered. After identifying these connected components, one representative token is selected from each distinct region, effectively reducing redundancy. In the second step, the temporal dimension is addressed by applying SCC again across the selected representative tokens from all frames, ensuring that overlapping semantic regions across frames are further compressed, resulting in a final set of tokens that comprehensively represent the video without redundancy.
What are the theoretical and practical benefits of using LLaVA-Scissor over existing token reduction techniques, particularly in terms of efficiency and representation accuracy?
Theoretical benefits of using LLaVA-Scissor include its ability to capture all distinct semantic regions through the Semantic Connected Components (SCC) strategy, which partitions tokens into non-overlapping regions based on pairwise similarity, thus avoiding redundancy and ensuring comprehensive representation of video content. Practically, LLaVA-Scissor demonstrates superior efficiency by performing token compression across both spatial and temporal dimensions, which allows it to maintain high representation accuracy even at lower token retention ratios. Experimental results show that LLaVA-Scissor consistently outperforms existing methods, particularly under extreme compression settings, achieving better performance at a 5% retention ratio than other methods do at 10%. Additionally, it effectively preserves essential semantic information, as evidenced by its performance on various benchmarks, where it shows increasing advantages as the retention ratio decreases. Overall, LLaVA-Scissor not only reduces computational costs, but also enhances the model's ability to understand and process video content accurately.
Describe the experimental design used to validate LLaVA-Scissor. What benchmarks and metrics were employed to assess its performance, and how do the results compare to other token compression methods?
The experimental design to validate LLaVA-Scissor involved evaluating its performance on various benchmarks, including video question answering benchmarks, ActivityNet QA, Video ChatGPT, NextQA, long video benchmarks, Ego Schema, Video Me, Video MMMU, and the multi-choice benchmark MVBench. The performance was assessed under varying token retention ratios, specifically focusing on how well LLaVA-Scissor preserved essential semantic information as the retention ratio decreased. Results indicated that LLaVA-Scissor consistently outperformed other token compression methods, particularly at lower retention ratios, achieving better performance at a 5% retention ratio than other methods did at 10%. This highlights LLaVA-Scissor's superior efficiency in extreme compression settings, demonstrating its effectiveness in maintaining model performance while reducing token redundancy. The experiments were conducted using an enhanced LLaVA1 vision model, ensuring a fair comparison against methods like VisionZip, PLLaVA, FastV, and DICOC.
What limitations or drawbacks does LLaVA-Scissor have, and how might these impact its application in real-world scenarios?
The LLaVA-Scissor method, while effective in reducing redundancy and preserving essential semantic information, has limitations related to its reliance on the similarity threshold, tau, and error tolerance, epsilon parameters. These parameters significantly influence the accuracy of the connectivity graph and the number of tokens retained after compression. If set too leniently, they may lead to the inclusion of less relevant tokens, potentially compromising the model's performance. Additionally, the method's performance is notably sensitive to aggressive token reduction, as indicated by sharp declines in accuracy when retention ratios drop below 35%. This suggests that in real-world applications where token budgets are constrained, LLaVA-Scissor may struggle to maintain high performance, particularly in scenarios requiring nuanced understanding of complex video content. Furthermore, the computational cost associated with the initial similarity computation could pose challenges in environments with limited processing resources, potentially hindering its scalability and efficiency in practical deployments.